So we're going to do an example with a gate. The idea is like a big dam where there's something that controls the water flow underneath of it. So this example is going to have something that looks sort of like this. That's moving up and down. And the bottom slope of the channel is 0.01. The bottom width of the channel is 5 feet. This is a rectangular channel, so m is equal to 0. The Manning's roughness coefficient is 0.015, and the flow rate is 300 cubic feet per second. So what we need to do is get normal depth and critical depth. So we don't know the depth yet, but I've got all of the rest of the information plugged into the spreadsheet here. So to get normal depth, we're going to goal seek this Manning flow rate. Okay, 4.42 and an energy of 7.28, a specific force of 175.3. Let's get critical also. We're going to set the Froude number equal to 1 by changing the depth. Okay, so that's 4.82 with an energy of 7.23 and a specific force of 174. Let's write all that down. For this example, I'm going to build sort of a table that shows all of our points of interest and the values that are associated with those. So the first value in our table, or the first point of interest, is normal depth. And we just calculated that that depth is 4.42, and the energy is 7.28. The specific force is 175.3. And then we did some calculations on critical depth, and that depth was 4.82, energy 7.23, and specific force, which we don't need it, but we'll write it down. Let's sketch that out to help us understand what's going on. So normal depth critical depth. So in this case, this is a steep slope. I should have pointed out that the Froude number is greater than 1 when the depth is at normal depth. And I haven't talked about this, but we need to know how open is this gate. So it's not a very good drawing to scale, but this dimension for this problem is going to be 4 feet. So, obviously as this changes, the gate opens and closes, the depth on either side are going to change. One of the things about this type of a gate is that the opening of the gate causes water to race down along the face of the gate, and as it tries to make this curve to break out, it actually lowers in depth past that, and it's could be described as something like a contraction coefficient, just like for an orifice. So if we know the diameter of an orifice flow and we wanted to calculate what the area of the water is that's flowing out of that, there's a reduction coefficient. And so for us, because we know the opening of the gate, we also know the depth of the water just downstream of the gate, just downstream. And so let's call this location D right here. And YD is going to be 4 feet times the contraction coefficient. And for that, it's 0.6. And that is going to be dependent on the gate. So this is a knife edge gate, so we'll use 0.6. So our actual water depth at location D is 2.4 feet. So what we're going to do is we're going to use that depth to figure out what the depth is upstream of that, and we'll call this point G. So it's probably worthwhile to go ahead and draw this out as a specific energy diagram. Okay, so we just, well, recently we found critical. That was 4.82. And we found, and that energy was 7.23 feet. And then we found the normal depth energy and depth. So and now we're interested in what is the energy here. So we've got a depth of 2.4 feet, and we're going to calculate what the energy is in the Excel spreadsheet, and then we'll use that energy to find the alternate depth that corresponds. So this depth is going to give us the energy, and then that energy is going to give us the alternate depth that corresponds with location G. So YG, let's find that out. We need to use a spreadsheet and do some goal seek. So all we got to do is just type in that 2.4 here. And that gives us a specific energy of 12.10. And so now we need to goal seek for the alternate depth to that specific energy. And to do that, to get the correct answer, we need to find a subcritical value. So notice that this is a supercritical value. We need to get a subcritical value, which would be the alternate depth. So I need to put in a first guess that's greater than the critical depth. And I'm just going to put in 10. So checking the Froude number is less than 1. Now what we're going to do is we're going to goal seek to get this energy equal to 12.1. Okay, so 11.69 is the depth, and the specific energy is 12.1. And because I know how this problem is going to work out, this is going to be a part of our delta x calculation. So we're also going to need to get the velocity of 5.13 and hydraulic radius of 2.06. So I'm also going to go ahead and copy this and paste special. I'm going to put the values in there, and that'll help us with our delta x calculation here in a second. Let's go back and write it down, and we'll sketch this thing out. So let's see. Section D has a depth of 2.4 and an energy of 12.1. We don't need the specific force there. It might be interesting in certain cases, but not this time. And then we need to figure out what's going on with section G. So it's going to have the same specific energy. The alternate depth of 2.4 feet is 11.69. And then we also need to know what is the velocity and the hydraulic radius for section G. And so the velocity is 5.13 and the hydraulic radius is 2.06. And so we can sketch this sucker out. Let's put in the sketch. So it's going to be, if we go far upstream, it's going to be at uniform depth. And if we go far enough downstream, it's going to be uniform depth. Between section D and the downstream section will be an S3 curve. And then from section G upstream, so I'm trying to draw these in the direction the control is. So downstream of the gate is going to be upstream control. So I started upstream at section D and worked downstream. And then upstream of the gate, at least for a little while, will be downstream controls because it's subcritical. And that subcritical in a steep slope is an S1 curve. Oops. At some point, the momentum will be reducing and reducing until it is equivalent to the normal depth momentum, and that will cause a hydraulic jump, and it will jump to uniform conditions from there. So let's call this section J. Let's label this first, I guess. So this is an S1 curve. And we'll call this section J. And so we need to know what is delta x. And to get delta x, then we've got to find out what is going on at section J. So this is a case of conjugate depths. And so if we get the depth that corresponds with the same momentum as normal depth, then that would be the conjugate depth. So we can sketch that real quick. So normal depth will give us the momentum that we're looking for, and that momentum will give us yj. That's the last step. So these two are conjugate depths, just like these two are alternate depths. So we need to goal seek again to get what's going on at j. So one thing we could write down now is that the momentum for section J is 175.3. We know that answer. And that's in cubic feet. So we need to have a subcritical answer. The conjugate of the normal depth will be subcritical. So our first guess needs to be subcritical, and I'm checking this fruit number is less than 1, so that's going to happen. So let's goal seek the force. We're going to set that specific force to 175.3 by changing the depth. and I got 5.24. This is going to be part of our delta x calculation, so we should take a look at the velocity and the hydraulic radius also. So we're going to do that, and then because I've got this hard-coded in the spreadsheet to solve it, I'm going to just paste this down here as numbers. Oh, you know what? I got these backwards. So let me put section G in area 2. I noticed because my delta x is negative, and then I'll put the values that I just looked up into section 1. That's where it was supposed to go. Okay, so our answer, delta x is going to be 69.1, and SF bar is going to be 0.0031. Let's do the math. We'll do that calculation by hand also. So section J, we just found that depth to be 5.24, and the energy there is 7.27. Also, we needed to know the velocity. That was 11.46, and the hydraulic radius is 1.69. So if we average those out, we get 8.3 and 1.88. Now we need to do the average slope of friction calculation. That's the rearrangement of the Manning equation. So the first value is the slope of friction, or sorry, the Manning's roughness coefficient, and then we multiply that by the average velocity. We do our unit correction, and then the average hydraulic radius to the 2/3 power. Squared. So doing the math, we get 0.0031. And then to do our delta x calculation, that's the downstream energy, or the energy at section G, minus the upstream energy. And then the bottom slope, minus the average slope of friction, gives us 691. So just to be really clear about it, one of the common places that people make mistakes is they'll try to do this delta x calculation, but instead of going from G to J, they'll try to go from G to the normal depth, and that won't work. So if you try to do that, you're going to end up with something pretty wild. That's just one of the common mistakes. So this problem looks a little bit different if the channel's a mild channel instead of a steep channel, and so that will present a different kind of challenge, but you can still go through and try and work the problem in the same way.